So today we're going to look at the derivative as a function. So on this graph, this black line that I drew represents f of x. So that's the function f of x. And then the red dashed line is a secant line between 2 points. So a secant line is a line that goes through 2 points on a graph. Okay, so I'm going to label this these points a little bit more. So this point right here would have x coordinate x plus h, and then the y coordinate would be f of x plus h. So that's just the corresponding y value. This point would be x comma f of x. Okay, so I'm going to draw a couple little things on here. So we're talking about that point and this point. Okay, so the secant line represents the average rate of change between those 2 points. So that is the average rate of change. So typically, we say the slope of the secant line is the average rate of change. So to go from that, it would be f of x plus h minus f of x divided by x plus h minus x. And this is really just the slope formula. So another way, to look at that would be we used to do f of x minus f of, actually, let me go back. From pre-calculus, the notation is usually f of b minus f of a divided by b minus a. So if you look at what we wrote here, this is really just a slope formula, but we have x plus h to represent the distance between x and x plus h. So if I simplify this a little bit, on the left, so if I were just to rewrite this, I would have f of x plus h minus f of x divided by h, because those x's would cancel out. Okay, so the derivative is the limit as h goes to 0 of f of x plus h minus f of x divided by h. So this is our big thing today. So this is the derivative. One representation of the derivative. And if you look at that, what it's saying is that if we go back to this graph here, as the difference between x and h, or x and x plus h becomes 0, we're going to have a different kind of a line. So these two black points on our graph that are noted here at x plus h, right there, and f of x plus h, and this point here, those 2 points would be brought together as h is shrunk to 0. So, because it would eventually be x right here, and then you're going to add a distance of h to get to this point, and that distance of h we're going to bring to 0. So what this is going to be called is the tangent line. Okay, so what I'm going to do is go into Desmos and just show you a quick demonstration of what that means visually. It's really hard to show on a static screen. So I'm going to go into Desmos. There's Desmos. So we have the function, whatever up here, 1/4 x squared minus x plus 1, fine. Okay, so the green line in this picture represents our secant line. So as let me slide, yeah, that one. So you can see as that all of these are secant lines between 2 points. As I bring those 2 points closer together, meaning as h becomes closer to 0, so I'm going to slide this slider for h. So you can see in the left column there, that number shrinking 2.8, 2.5, and eventually I get this thing to 0. And you'll notice that my line sort of goes away at 0. There's a reason for that. So h is 0 in that case. Well, that type of line, if I just back up a little bit, it doesn't really look like a secant line anymore. So it looks like it's not going through 2 points. It looks like it's going through exactly 1 point. So as h approaches 0, that is what's going to happen. This secant line that cuts through 2 points is going to be going through exactly 1 point on our graph, and that's called a point of tangency. So if I overlay those, I'm trying to get that right on there. Pretty close right there. Okay, it disappears. Then I can turn on the tangent line here. So the tangent line that I'm moving here, you see how the slope of that, the slope of the purple line follows the slope of the function at that point. So this is what we call the derivative. So the derivative is the slope of the tangent line. So again, the secant line is represented by going through 2 points, and the tangent line is a line that goes through exactly 1 point on a function. So that's what we call a point of tangency. All right. So there are several ways to write this. Another way you might see it written would be, use a different color here, the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, so once you, if you were to apply this to a function, the resulting function is the derivative. So we use the derivative to find the slope of the line tangent to every point of f of x. Okay, so if I just back up, go up here again, if we take the average rate of change, which is the secant line, and shrink the difference between those 2 points to practically 0, then we end up, and then we take the limit, we end up with the derivative. So the resulting function is the derivative. Use it to find the slope of the line tangent to every point of f of x. So this entire section, that's what we're going to be talking about, is just derivatives. So let's put it into practice. So here's an example. And I did choose a little bit more complicated example as our first example, just so that you can see how it works and what you'll have to do here. I know it doesn't look complicated, but that fraction makes it a little more work. Okay, so f of x is 3 over x, and it says find f prime of x. That's how you read this function here with a little tick mark. That is f prime of x. And then we're going to find the line tangent to f of x at x equals 3. So just to remind us, the limit as h goes to 0 of f of x plus h minus f of x divided by h is, that's what we're going to use on this function f of x. So I'm going to move that to the side here, color it a little different. Let's start red. Okay. So we're going to take the limit as h goes to 0 of f of x plus h. So wherever there's an x in our function, we plug in an x plus h, subtract f of x, and divide all of that by h. So again, like most of these sections, this is an algebraic exercise. So in the numerator, we have to have a common denominator. That common denominator is x times x plus h. So I would have the limit as h goes to 0. I will show this. So we're going to multiply this by x plus h and this side by x. And let's do that first. So in the numerator of the numerator, I would have a 3x minus 3x minus 3h, all divided by x times x plus h. And you'll notice that sometimes I will distribute that x times x plus h, or whatever is in the denominator, and sometimes I won't. Typically, I won't do it until it seems like I might have to. So you get a feel for when you have to do that. All right, so this h in the denominator, if we basically factor out everything in from the numerator, and we'd be left with the 1 over h. So this is times 1 over h. And I'm going to repeat that step a lot. Okay, in the numerator, 3x cancels. We also have h as a cancellation. And yeah, that's about it. So if I were to rewrite this as h goes to 0, because I can plug in a 0 now for h, because that's not going to give me a discontinuity or anything like that. So I would have negative 3 over x squared. Okay, so this function is the derivative function. So it says find f prime of x. This is f prime of x. Then find the line tangent to f of x at x equals 3. Just give myself a separation line here. Okay, so I'm going to set up these problems the same way every time. So f prime of x, I just like to have a clear list of what I'm doing. So it's negative 3 over x squared. To find a line tangent, we're going to use, the easiest form of the line to use is y sub 2 minus y sub 1 equals m times x sub 2 minus x sub 1. So that's just the point slope version of this. That's going to be the go-to form of a line when it asks you for a tangent line. Okay, so what do we need for this? We need a slope. Well, this is my slope function. So f prime of x represents the slope function. Now, so to get the actual slope, we plug a 3 into it. So f prime of x equals negative 3 divided by 3 squared, which is negative 3/9 or negative 1/3. I need to clear up that. So I plugged in a 3 here. Okay. Next, so I have the slope, it's negative 1/3. Now I need to find a point. So the x value is given to us, so I know that x is 3. So I need to get, what value comes out of the function when I plug in a 3. So I'm going to check f of 3. Remembering that f of x is 3 over x. So that would be 3 over 3 or 1. Okay, so these are the things that we have here. We have an x value of 3, a y value of 1, and an m value of negative 1/3. So we just plug these things in, and we don't have to simplify it further than what we do in this initial step. So I will plug those in. So I'd have y minus 1 equals my slope of negative 1/3 times x minus 3. So that is the equation of the tangent line at x equals 3. Okay, so we're going to look at this problem in one other way. So there is a second way to look at this. So if we want to find the derivative at a point, which is what we just did in the last problem, we just looked at the derivative function and used that, but there is sort of a shortcut to it. So the shortcut, sort of, is the limit as x goes to c, so that would be your point, of f of x minus f of c divided by x minus c. So if we do this right, it will give us the same solution we had from the last problem. Okay, so our c value is 3, so we're just going to plug that in. So over here, I'll use a different color. The limit as x goes to 3, because that's our point in question, of f of x minus f of c. So f of c is 3 over 3, or 1, divided by x minus c, so that's x minus 3. Okay, so in this problem, we don't have the issue of the h to deal with, it's just this x. So we are going to simplify the numerator. Okay, multiply both of these by x, and we would get the limit as x goes to 3 of 3 minus x divided by x. And then I'm going to factor out this numerator. And so I'd be left with 1 over x minus 3. All right, so this is just algebraic manipulation stuff. So x goes to 3. Factor out this negative 1 in the numerator to get x minus 3 over x times 1 over x minus 3. Remove this discontinuity, and we get negative 1 over 3 if we plug in an x. Okay, so this is my f prime of 3. This is also my slope. So we're going to use all these terms interchangeably. Okay, so we have these, that value came out to negative 1/3. And so again, we would have y minus 1 if we plug in a 3. So this would be y minus 1. Slope value is 1/3. And so we do, in fact, get the same result. So that would be the way to jump to the derivative at a point, but it doesn't really matter which one you use. Okay, so for notation for the derivative, there is a wide variety of notation we'll use. So I'm just going to write these all out as an equivalency so you can see they're all pretty much the same thing. So these are essentially all slopes. So it's just kind of different notation for that same idea. So f prime of x, this would be the notation that we got from Isaac Newton. Then we said the limit as x goes to c of f of x minus f of c divided by x minus c, which is the same thing as the limit as h goes to 0 of f of x plus h minus f of x divided by h, which is the same thing as y prime, which is the same thing as dy dx. And this one is from Leibniz. So calculus was developed by two people simultaneously. Neither of them knew the other was doing it, which is kind of amazing. And so those were Newton and Leibniz. So we have these two different notations which describe the same thing. And one's not better than the other. It's just depending on the scenario. Sometimes it's easier to use the dy dx. Sometimes it's easier to use f prime of x. And the way we'd read this, this Leibniz version, I'll actually write it out because it's important. So this one means the derivative of y with respect to x. So if you're reading that, that's a way you could say it. Okay, so I'm going to do just one more example. I do warn you that these problems they can be kind of long and tedious, but please work through them slowly because there's a lot of places to make algebraic errors. So as long as you work slowly, you'll avoid a lot of that. Okay, so this one says find f prime of a and the equation of the tangent line. So it's just like the other two examples we did. So we take the limit as h goes to 0. Also, you can't drop this limit notation, so this has to be in every step until you actually evaluate at h equals 0. So f of x plus h. Okay, so that is f of x plus h. And then we subtract f of x. And I'm going to put this in parentheses so that I remember to distribute the negative sign. And that's all divided by maybe line h. Okay, so we just keep simplifying this until we get something we can work with. Basically until you can plug 0 in. Okay, so this would be 2 times x squared plus 2xh plus h squared plus 10x plus 10h minus 2x squared minus 10x. All over h. Okay, distribute the 2. And this problem is one of the assigned homework problems, so you don't have to do this one on the assignment. Okay, really trying to avoid making a mistake so I don't have to do this problem later again. So that's over h. And if you look at that, you can now cancel out some things. So we can cancel out this 2x squared. We can cancel out this 10x. And we're left with the rest of that. So normally I would skip a step here and factor out the h between those two. But what I'm going to do is do that, a separate step, just step for clarity. Okay, so now you can see that all the terms in the numerator share an h, so now we can take that h out because we're trying to get that h in the denominator to cancel. The whole point of this exercise is to get the h in the denominator to cancel. So we take the x out, oh, not the x, we take the h out. Get that, let's cancel the h's. And in this case, we can plug in h. So in the numerator, that would zero out the 2h, so we just have 4x plus 10. Okay, so that would represent my f prime. So I'm going to change colors over here. So f prime of x is 4x plus 10. So if we're going to use the point slope form of the line, we need a point and a slope. Isn't that amazing? So we generate a slope so that we're talking about at a equals 3. So f prime of 3 equals 22. And then we're going to plug in a 3 into the original function. So this would be 18 plus 30, so 48. Okay, so again, we have all of our parts we need. We have an m value, an x value, and a y value. So this would be y minus 48 equals 22 times x minus 3. So this would be the equation of the tangent line.